All right, so let's make some AIs. The simplest one probably is to start with simple machine learning. And all you need is a Python environment of any kind. I like to use Google Colab because any student can have it with just a browser and a Google account. And so it's consistent for everybody. So we're going to use TensorFlow, and it doesn't really matter which version, so I'll just put that here. When you first run it, it's going to create a container, a Docker container, I think, for you to use. So it takes about 30 seconds to spin it up, and it gives you a pretty good bunch of resources, enough that you can do quite a lot. And then it's going to run this code, and that's not going to produce any output. But anyway, then I'm going to make a linear relationship. So I'm just going to feed it some data where x goes -1, 0, 1, 2, 3, 4, and y goes -3 up to 7. So if a human looks at this, you can say, well, it looks like when x gets bigger, y gets bigger. And if you look more carefully, you can see every time x goes up by 1, y goes up by 2. So the equation is y equals 2x minus 1. That's what this relationship is. But what I want to do is have artificial intelligence discover that relationship without a human programming it in. And so all you really need is this one here. Um, and that's why everything is easy in Python, because Python, other people have written libraries that do all the work, and all you have to do is learn how to use the library. So we're going to use TensorFlow and NumPy, and then Keras is this model. So I'm going to here's my data, X and Y, and it's just going to make a model, and I'm going to use a measure of loss as the mean squared error. So it will start with random parameters. It's going to have one neuron, which takes X as an input and does a linear transformation on it to go to Y. So it's got a slope and an intercept are the two parameters. It will assign them random values, and then it will do stochastic gradient descent, SGD, which is a general optimization program. This is incredibly simple. You have a model that uses some parameters. You just start the parameters at random values, and then you have some measure of loss, which in this case is going to be the mean squared error. It's going to take the predicted y value and subtract the y value that the right y value. And so the loss is 1197. So what it does, it calculates the current loss, and then it uses partial derivatives to figure out what direction in parameter space would make the loss smaller. Assuming it's a straight line relationship, it takes a small step because any curve is a straight line if you only move a small distance. So it takes a little hop. Now the loss is 9, now it's 7, now it's 6. Each hop makes it a little smaller. So it will converge on the best answer eventually. And you'll see after 500 steps, which it calls epochs, the loss gets really small, like down to 10 to the minus 5. So when it's done, it's finished. Now all I did was I had predict the value for 10. And the right answer is 2 times x minus 1, which is 19. So it got 18.98. So it got very close, within 1% of the right answer. Even better than that. So that's it figured this out. It's figured out what values of M and C work to make this model fit. And you can see the weights if you want. Um, and if you do, you'll see the weights are quite good, very close to 2 and very close to minus 1. So it's good at that. Now we can try adding some errors to it. I just added some random noise to the Y value because this is kind of unrealistic that you have absolutely perfect data. So I'll put in that data, and you don't really have to, but I'll comment out the previous line. All right, so now I just moved them down by a little. So here it goes again. It started with a loss of 40, 32, 25, so the loss is going down. By the way, you notice it has a built-in AI in this thing, so you can use AI to help write your code too, which I'm not doing here, but you could. And so the loss is going down, down, down. And get down to the end here. Still running. Okay. But the loss is getting down to 0.004, and it's not getting any lower because there's actual noise in the data. It can't perfectly fit that data. It's going to have some irretrievable loss, but again, it's quite close, 18.95. So it works pretty well. Now, you can try fitting data that is not a straight line. Here's x squared minus 4x minus 5. So if you try to put a straight line through something that is not a straight line, Get back to the top here and put that in. All right. Now, this is like the large language models. This is what I've been telling you. It's stupid. So it's putting a straight line through something that is not a straight line, but it doesn't know that. So it just goes for the minimum loss 80, 65, 54, and so on. And it's going to end up with a terrible loss value, of course, but it is going to put a straight line through those points, the best straight line it can find. It is not smart enough to know that it can't do this. This, by the way, happened to Donald Trump in his first term about the uh, COVID pandemic. At one point, you remember early in the pandemic, he said it's all going to vanish by Easter. It's just going to vanish because one of his advisors used Excel and fit a high order polynomial to the data points of how many people had COVID. And it fit a high order polynomial that waved up and down, and it actually went to zero, like on the date of Easter, because it fit a silly curve through the data points, fitting the noise as well as the data, overfitting, and then had wild predictions. It didn't follow the trend, the kind of thing that can happen. And like I said, that's why humans have to add intelligence to it. So then we can try fitting a more complex curve. We can try a better model. Instead of just having one neuron, we're going to have input come in and then feed to a hidden layer of neurons, and then another hidden layer of neurons that process it, and then the output layer. So this is a neural net. And again, it doesn't take very much data to do it. It doesn't take very much code to do it. And what we're going to do here is take a curve. Let me just make a new block of code down here. There we go. All right. So the curve is x times cosine x plus noise. So it's just a wavy curve. And I'm going to take one input, which is x, then a hidden layer of 64 neurons to just process it, then another hidden layer, and one output layer. So I have a lot more parameters. So now if you run this one, it'll show you how many parameters there are. I have two parameters of the input, x, slope and intercept. Then I have 128 parameters, slope and intercept for each of these 64 neurons. Then 64 squared times 2, this number, 4,000, then 65 in the output. So total number of parameters is now over 4,000 parameters to adjust. And so it's still only taking a few milliseconds to do a step. It initialized all those 4,000 parameters randomly, and now it just uses stochastic gradient descent to move in a direction that causes the loss to fall. And there goes the loss falling. And after 100 cycles, see, it does a pretty good job. I wonder if there's any way to turn this thing off. Anyway, so it does a pretty good job fitting it, which in principle, 4,000 parameters are enough to fit anything, you would think. Right, and now you can play games with it. Like, for example, suppose I don't want two hidden layers. I wonder how good a fit I can get with just one hidden layer. I could just comment out one of these layers to make a simpler model, and now it's going to have many fewer parameters. Now it's only got 195 parameters instead of 4,000. But it can do it. Loss goes down and down and down. And when it's done, okay, we get that, which as you can see is a much more crude approximation of fitting it. So you can play games here and try various models, see how well they work. This shows you the fundamental concept of how you do this thing you can call intelligence. It finds the pattern in the data without a human having to do that step by just optimizing the parameters. And there's a few more you can do this way. You can do computer vision here. Now this one, we're going to take, this is the one I talked about before, where we sort the images. You take input images that are 784 pixels, I think 28 by 28 pixel images in grayscale. So each pixel is a number from 0 to 255. You just separate the pixels out as independent measurements, run them through one layer of neurons, and then sort them into categories like coat, sneaker, and bag. Again, it only takes about 10 lines of code to do it. And when you're done, it can actually get an accuracy of like 87%. Now, the way you do this is you have a bunch of input data and you sort the data into training and test sets. You train it on part of the data and then you test it on some of the images it's never seen before. That's why the training will typically do a little better than the test. And so you can view the results. And here, there's another thing to understand. It doesn't give you a single output. What it does is it gives you an analog signal at each of the 10 output neurons. So the first entry um, is in fact type 9, category 9. And here's the output of the neurons. It has like a 2% chance of being category 7 and a 96% chance of being category 9. Here's another one. The right answer is 7, but in fact, it's 0, 1, 2, 3, 4, 5. It determined it had a 72% chance of being a 5 and only a 27% chance of being a 7. So the actual output is these varying signals, and you pick the one with the largest signal and call that the categorization, but you can tell when it's not sure. These outputs are similar in size. This is one where it's pretty confident. So that's what it really does. And you can see this one here, it could categorize. This one here, it couldn't decide if it was a shoe or a sandal, because how could you? That's hard to tell. So anyway, now if you train it more, its accuracy will improve on the training set, but on the test set, it will not improve. So this is overtraining. More precisely modeling the exact images you trained it on, but it is not doing any better on new images it's never seen before, so you're fooling yourself. The increased effort and the increased accuracy here is not reflecting an increased ability to actually do the job on new images. All right, so that's a fun one. And the next one was amazing to me. Deblurring, you can also break a CAPTCHA, you can sort distorted images into categories, but the deblurring images is the one that amazed me. Someone just did this as a photography exercise. They uploaded an array of images taken with different cameras in focus and out of focus. So I want to train it to deblur images. And I have a database of sharp and blurry images for it to learn on. And you can do that. You can, again, you split it into 80% to train it on, and you save 20% of the images to test it on later. And when you run it, if you give it 5 epochs of training, this is going to have 17 million parameters because it's processing full color images, which is a lot of data. And when you do that, if you give it 5 cycles of training, and each cycle takes it takes about 5 minutes to go through 5 epochs of training. It's quite a job. And when you're done, the results are terrible. This is the original blurry image, this is the deblurred image, and this is what the model produced. So 5 epochs of training is not enough at all for it to determine all 17 million parameters. So what you have to do is give it more training. Originally, I did it by letting it run for an hour and a half, which is the maximum you can possibly run a Google Colab instance. But then a student pointed out to me, you can use GPUs in Colab. There's limitations on how much you can do this with the free version, but you can turn on a graphics processing unit, which makes it much faster. And if you do that, you can then train for 100 epochs, and it will only take a few minutes instead of the 70 minutes it takes with the CPU. And after 100 epochs of training, it actually gets pretty good. This is the blurry image. This is the deblurred image. This is the original sharp image, and this is the deblurred image, which you see has kind of got halfway there. So I was very amazed that with just the amount of resources that Google gives you for free, you can actually do this job to some extent. So those are a few things to try getting basic machine learning tasks going. I'm going to stop this video.